So good afternoon, everyone, and welcome back to second session of the workshop, going on to the second day or the final day on best practices in chemical crystallography, data evaluation, and diagnosis. So we will try to give you in this workshop about what are the best practices you can do to improve your data, and what are the diagnostic plot you can look at, and what you can infer from them. So if you don't know me already, so I'm Dr. Pratap, product manager and application scientist for India, Middle East, and Asia Pacific. So if you have any crystallographic related, single crystal diffraction related questions, so you can just contact me using this ID here. So along with me today, again, my colleague is joining from Germany, who will take you through the diffractometer, Dr. Carsten Lenschik. Carsten, can you please
Mhm.
introduce yourself?
Yeah, thank you. So, as Pratap already said, my name is Carsten Lenschik. I'm the new application scientist in Karlsruhe. So I'm basically working in Europe, Africa, and near Middle East. I did my PhD in Würzburg, and after that, I did a postdoc at the TU Dortmund, and I joined Bruker in January this year. So I'm very excited to be part of this cool team, and now to present you also or give you a talk together with Pratap about the best practices in chemical crystallography.
Yeah, thank you, Carsten. So if you are wondering where I'm sitting in Bangalore in our Center of Excellence office. We have started the recording, so that means we will be recording this session, and then we might use this for our marketing purposes, or maybe we put this up on our website and so on. So if you are not okay with this, so feel free to exit, or because it's obviously gets recorded otherwise. Don't feel shy. So ask us the questions. So whatever the doubts you have, please raise your hand or use chat panel. And if you can unmute yourself and also discuss with us during the course of this session. Also, if you have doubts afterwards, so you can write to us by provided email address, both me and Carsten, or any of our application colleagues. So you can directly write to us and then get the answers. The agenda for this session, this is the second day, the same session, same workshop we are doing. The idea is to give an opportunity for the people who have missed yesterday or who have attended the parallel session, so they can attend this session today, or the person who has attended to understand more, so they can attend again to get the best practices or to get the art of doing best processing of your data. The agenda for this is I will take you through the sample preparation. I will show after the sample preparation, maybe Carsten will take you through the diffractometers. He shows the screening and first scan strategy versus the matrix strategy, and then he will set up for data collection. And once we learn the art of collecting efficient data, I will go through the efficient processing of your data and diagnosis of those plots. What does that mean and what you can infer from them. So let's begin with the sample preparation, and you know why you have to do the sample preparation, because this is the most important part of your crystallography or single crystal diffraction. The crystal has to be good because machine can't do any magic. So if your crystal is good, obviously your data will be nice. Of course, machine will take care about your intensity and then your detector quality, your enhance the quality of data, but it can't do magic. Okay, so that's why the sample preparation is the most important part, and it has a massive influence on your overall data quality. What's the good sample preparation is you should mount a properly sized crystal and then properly mounted without having too much oil or glues or any adhesives into your crystal. How does it directly affect on the data is it minimizes your absorption effects on your crystal or overall data. It reduces your background scatter, which might be hamper your weak reflections, and it overall improves your data collection strategy and overall data quality. So if you start with your bad crystal, so then you end up with a bad data. Even your parameters like R value, R int, R sigma, everything can be on the higher side. But if you put an effort in preparing the best sample, so all of these factors will be having the better values, and then you end up with a very good quality data. So then the first question is then what should be an ideal sample? Ideal sample for a single crystal is ideally a crystal should be single. If it is a twin or if it is there are two crystals mounted, so then we have the software to take care. So that's a different story. But ideally, you want to have a crystal which is a single crystal which should not have any cracks or any precipitate or impurities sitting on your crystal. And ideally, you should have a crystal which is having a uniform size like this, spherical. You don't get the spherical, you might have a regular plate-like or needle-like, but try to cut the crystal to the isotropic shape so that you can have a better scaling or better overall quality of your data, not much change in the diffraction volume or not too much absorption effect. So it should be isotropic in shape, and size of the crystal should match your X-ray beam diameter. So if you mount a very big crystal, then you end up with a very large absorption effect. If you have a very small crystal, so then you do not have any choice. So you need to live with it. So you can use smaller beams, but if you have only one diffractometer and only one size, so then you can't do it. So you need to live with it. But if it is big, try to cut the crystal according to the size of the beam. Just to inform you, what are the general X-ray source we have in Bruker? We have got 1 kilowatt seal tube source. We have got 3 kilowatt seal tube source, which comes with the triumph, which enhances the intensity. So without the triumph, the beam size coming out of our seal tube, either it is 1 kilowatt or 3 kilowatt, is around 400, 500 microns. So you can mount the bigger crystal, like around 400 micron crystals. But if you use a triumph, the intensity is improved and also you get the smaller beam. So you can go up to 200 micron crystal. So ideally the crystal for seal tube will be around 200 micron. But then you have, if you have got the microfocus sources, whether it's the first, second or third generation, you get a beam around 100 micron. So ideally the crystal should be around 100 micron. So you can measure the crystal on the video microscope. Carsten will show you that where the beam is coming and what should be the crystal size. But ideally you should mount a crystal which is around 100 micron for a microfocus tube. But then if you are using, for example, metal jet source, so then ideally the beam size is around 75 micron, 70 or 75 micron. So you try to mount a crystal around that size to avoid unnecessary absorption effects and so on. And ideally the crystal should be mounted like this without too much of oil or too much of glue, so which might also leads to a lot of background. So the ideal simple properties or the points we have mentioned here, so make sure you do that. So then I want you to learn how we are actually doing the crystallography, or in application lab, how we take care of the crystal is just explained in this slide. This is because what we have got one, any crystallographic lab, we would recommend that you would to have a very good microscope with a polarizing analyzer capability, because if you look your one of the property of your single crystal is it should be birefringent, or maybe it extinguishes the light. What does that mean? When you move the crystal under polarizer, so you should be able to see one time the light should pass through the crystal, one time light should be blocked by the crystal. So that is a property of a single crystal. So that's why the polarizer is necessary to look your crystal. And also it gives you an advantage of looking through the crystal if there is any crack or something, so you can discard those crystal and try to mount a crystal which is without having any cracks. And then you would like to have a different kinds of tools to manipulate your crystals, with some bigger grip and with some smaller grips, some acupuncture needles and some X-Acto knife. So this bigger grip with a needle will help you to manipulate with a little harder crystal or a bigger crystal. But if you are working with very thin needle or flaky or protein crystals, so then try to use these acupuncture needles, because then there is a high chance if you use this bigger grip with thicker needles, so you might break the crystal. So that's why you use these acupuncture needles to work with the fragile crystals. And then why do you need this X-Acto knife or a razor blade or a scalpel is because you want to cut your crystal according to the size of the beam. So these should be there in your crystallographic mounting kit for sure. And along with that, you will get different mounting accessories. So the goniometer head, which comes with now with a magnetic base, which is ideal because you don't disturb your goniometer setup too much. So this will be always fixed onto your diffractometer. You just play with this crystal cap, just putting onto the magnetic base here and then take it from there. Otherwise, previously what you were using like this, and then every time you are tightening this grub screw, and then after some time this grub screw loses its strength, and then you are just collecting some data which is having a lot of vibration or movement in the crystal, so which is not good. To avoid this, have this magnetic base, which is strong magnetic base you get, and then you just play with these kind of different kinds of mounts. So there are some steel pins and there are copper pins. Copper pin has its own advantage because it's a better thermal conductor, so formation of ice will be minimum here. And then you get some capillaries and loops, which I will explain later. Capillaries is it's of special glass capillaries, which will be used to mount your air sensitive crystals. There are some adhesives available. So most widely used is the paratone oil, so which is viscous, which also does not dissolve so many crystals. So that's why paratone is widely used, which also have a lower background to your X-ray. So that's why we use paratone oil to stick the crystal into the loop or metagen mounts. Whereas if you think the paratone oil is not suitable, you can use silicone oil or you can use grease sometime to mount your crystal. This is some videos my colleague from Karlsruhe, Dr. Tobias Stutzer, has put in to show you that how we mount the crystal, because we can't come to your lab now. Now we can show only through video. So they have collected some videos and put it in for you that how we are taking care of the crystal. So what we do is actually we get the we work under microscope. We just take a fresh glass slide and then take the crystals, put some crystals on the glass slide first and try to pick up the right candidates for our measurements. So he is fortunate, he got plenty of crystals, so he is choosing out of thousands. If you have only 3 or 4 out of this, you want to pick up which is the best, which is not having cracks or anything, and according to the size of the beam, you want to take the crystal. If it is big, it's okay, you can cut always, but he is now initially trying to pick those crystal which is having a particular shape and a particular size, and then keeping it aside as the first attempt. Once he does this, and the second step, what he does is he will take a drop of paratone oil with that same pin which he used to put the crystal, and then put a drop of paratone oil there on the side of the glass slide, and then trying to take those crystals which he selected into the oil. So what is the purpose is he wants to clean those crystals. If there is any secondary crystal or impurities or a precipitate or anything sitting on that crystal, he want to wash that off and he want to take a pure single crystal. Another advantage is by doing this, so he's making crystal smooth if he wants to cut the crystal. For example, just imagine if you are cutting a dry crystal, so sometimes it might spill off from your glass slide while you are applying some pressure. If the crystal is smooth and it is in oil, so you can cut the crystal very smoothly, and also where if at all it just shatters, so it just within the oil, it will not fall off from your glass slide. So 90% of the time it doesn't happen, so it will allow you to cut your crystal smoothly. So that's an added advantage along with washing your crystal, and also it acts as a protectant for your crystal as well if it is air sensitive or something. Once he does that, he will look under polarizer under the microscope. So he wants to make sure whatever the candidates he has chosen is good enough or the right ones. And if there is any cracks or anything, so he just want to make sure that he is not choosing those kind of crystals. So look at here, these 3 crystals, which is darker now, once he rotate the polarizer, now it is becoming bright. So that means light is passing through. And then the other crystals are getting darker. Like for example, this, now it is getting brighter if you rotate on the other direction. This is actually the typical property of your crystal. So which extinguishes the light when you rotate around polarizer and polarizer microscope. Okay, so once he does all these things, so now he is ready. So he wants to choose the mounting setup. So that is the loop. So he can choose different kinds of loop. These conical shaped loops will be is better for the better stability, so it does not give you too much vibration, and then shorter length of these pins also is good because which gives the stability. At the same time, the shorter loop length is also very is recommended because it does not give you too much vibration into your crystal. And just the and if you see these kind of micro-meridian mounts, so this actually is come with a kind of a ink pen nib, so which gives you the stability for your crystal, which will not have this vibration or movement while you are processing or collecting your data under low temperature. So that's why it has these kind of shapes, and it is available in different sizes, so you can use for different size crystals, different size of loops. You also can use regular Hampton loops, which is made up of nylon. Of course, you can observe slightly more background compared to this micro-meridian bonds, but yeah, feel free to use this as well. But the copper pins will be very nice with the magnetic base, which will help you to have a less ice formation compared to this steel pins. Okay, so once he chosen the micro loops, his crystal is ready. So he has taken the loop now, and the aim is to mount or pick up the crystal onto the loop. So you can do two ways, because one, you can push your crystal outside of this oil using the your tool, the acupuncture needle or something, or else you can directly play with your loop as well. In this case, my colleague is taking directly the loop and trying to push the crystal outside of the oil. The aim is to minimize the he wants to mount the crystal with minimum amount of oil. So he don't want to mount a crystal with lot of amount of oil, so which will have a lot of background. So while doing so, he also picked up the crystal, so he's happy, and he is going for the diffractometer for the mounting. So before he go to the diffractometer, or we go to the diffractometer, I want to stress with some couple of slides that what is the impact of your sample preparation. So you might be wonder what dog is doing here. Because actually, this dog is the donor of this crystal. This is a kidney stone of this dog. Actually, it's one of my colleagues, Michael Roof's dog in USA. So he is a crystallographer. He got this kidney stone into the lab, and then he wanted to see whether he can find some single crystal out of this mass. What he did was he just broke that mass in under the liquid night under the microscope with the paraton oil, and then broke into several pieces. And then he could see, when he rotated the polarizer and analyzer, some transparent crystal on the edge of these masses. So then what he did was, like for example, here you can see one of them. So what he did was he picked up one such things and then put it on the diffractometer and solved the crystal within 5 minutes. So a lot of time he spent almost 20 minutes to find a crystal, but then collection and processing just took him 5 minutes. So the inference or the information I want to give you here is, the sample preparation is the most important point. Don't be lazy at the beginning. So pick up the right crystal, and then your life will be easy. Your processing or collection of the data will be much easier. So 20 minutes for data crystal selection, and then 5 minutes he used for just processing his data. So that's the advantage if you if you get good crystal. So then there might be in audience might be dealing with some air sensitive crystal. Do we have some tips? Yes, what we do is generally, if you are quick enough, if you have a quick hands, what you can do, you put a drop of paraton oil, put some crystals along with the mother liquor, and try to pick up the crystal as fast as possible and freeze it under liquid nitrogen in the diffractometer. So that's a quick and easier way. If you want to go slightly difficult way, so you can do and mount in a capillary the crystal along with the mother liquor and seal it from both sides and collect the data. That's the second. Third is, you can also get this kind of X-stamp. This is invented by Dietmar, Professor Dietmar Starke from University of Göttingen. It's also available. So then you can use these kind of extemp setup. So for mounting your crystal, what it does is it constantly blows the liquid nitrogen into your glass slide. So you can pick up so that your crystals is not exposed to the air or high temperature. So you can get this crystal enough time for mounting, and then you can freeze that under liquid nitrogen. This is also another way of doing it. So once you mounted your crystal, so make sure that your diffractometer is in a perfect shape and ready for your experiment. So make sure your video microscope is properly aligned so that you can center your crystal. Make sure your goniometer is properly fixed onto your goniometer head is properly fixed onto the goniometer with all these magnetic base is tight and strong. And then if you are using the right collimeter, because if if your colleague might have used for some other experiment, if he might have changed the collimeter, make sure you are having the right collimeter. And if your beam is proper, and then you just go ahead and your low temperature is running properly without any ice or anything, whether it is aligned properly, whether it's how far it's a distance from your crystal, make sure everything is ready and then start with your measurement. I think now we'll go. Now I stop here and I will take you to Germany, where Carsten will show you how to process, screen and process the crystal collection of your data. Thank you. Carsten is yours.
Yeah, thank you very much, Pratap. So as said, I will take over from here. Just let me share my screen. Right. And there we go. I hope you can see it now.
Yes, I can see.
Okay, perfect. So as Pratap already said, we already mounted a crystal successfully on the loop and put this loop on the goniometer. And we have two kinds of different goniometer heads. As you can see here, we now have the manual one, and I show it in the camera. So as you can see here, you have some different screws. So you can center and align it by using a special screwdriver, which I will show in a few seconds, but by just turning those screws. Of course, we also have an automated goniometer head, which we call AGH. This is most common in protein works, where they just screen a lot of crystals and want to do it full automatically. So, but of course, this would be also an option to do with normal crystallography. But as you can see here, you won't have any screws, but this is fully automatic. If we have the manual goniometer head, you, as said, need a certain tool, which is this. And as you can see here, it is some kind of screwdriver, which is perfectly fitting into those screws on this goniometer head. So what I will do now is I can adjust the height on the upper screw, and we'll do that to get it aligned, as you can see here. What I will then do is I do the same for the left and right. So I just put it first into the center, which looks mostly okay. And what I would then do is I would click on 90 degree. Once again, we will put it, we'll align it left and right. And then we just click it again to ensure if it stays in the center, which it does. I normally, and especially emphasize if you have very, very small crystals, would do a second 180 degree scan and carefully check if at all time the crystal is in the center or stays in the center circle of this goniometer. The same I would do also for the other alignment. So you just go here and do once again 180 degrees. And you see that it is now perfectly centered. So we close this plugin. And what we will then do is we will start with the fast scan. I will close the door. So as you see, I had the experiment from yesterday. I will get back to it in a few seconds, don't worry. So what I will do then is we will do a fast scan in different, in the sensitive mode and without attenuation. I will come back to that also in a few seconds. And we just click execute because we now want to get a first idea about the diffraction quality of the crystal itself. So we have to wait a little bit because now it tells us, okay, it has to ramp up the generator because it was in standby mode. It's always listed here what it is currently doing. You can, of course, also check on the BIS. This is this Bruker instrument server. And there you get all the information so far that you need. So here you see it's stabilizing the generator. Currently, we're using molybdenum. And as you can see here, it is ramping and stabilizing. The goniometer position is at this position right now. Since we don't attach the automatic goniometer head, this is assigned as offline. And we do room temp measurement. So the cryostat is attached, but it is not active right now. So it is done stabilizing. And in a few seconds, it will start the measurement.
Okay, what can you explain what source and what detector you're using?
Okay, so right now I'm using the IMUS 3.0. So that's a microfocus source. And the shape of this detector might already tell you. So we're using a C14 photon 3 detector. So we have 3 different sizes. It's this, at least for the photon 3. So it's the C7, it's the C14, and we have also the, I guess, M28. C and M is for chemical or for biological or specified for those 2 types, because in biological crystallography, you most of the time use copper or softer radiation, while for chemical crystallography, most of the time molybdenum is used. And this has to be accounted also for the conversion material, because the harder your radiation, of course, the more it can go through your conversion material. So you have to get a little bit thicker layer of this if you want to go for hard radiation like silver or indium. Okay, so what we do now, I would let it run and just look closely on the frames passing by. So what I would do is first I have to check how well are the spots separated. So you don't want to have them overlapping. In case they do, it's either twinned, and you can try to increase the detector distance. So that would be the first thing I would do. You see now here, the spot separation, as far as you can see, is nice. So we can even decrease it. I guess we currently measure at 50. We can also decrease it to 40 millimeter, and we will still get some very nice spot separation. The second thing I would check is the shape of the spots. So what we want to have them as isotropic as possible, meaning we want to have round circle-shaped spots. So we don't want to have them elongated. This is a little normal because it goes more to the outer high resolution part of the detector, but you want to have them as round as possible. To check them in more detail, you can also go to the evaluate and view images. And here you can browse step by step through the images. So you can use the resolution circle, which I would always do afterwards, or with some of the frames, because here you get an idea how well your crystal is diffracting and to which resolution you get signal. So here, even beyond 0.8, I would suggest you see here down already that you will get some signals. Second, you have this region of interest tool where you can draw a rectangle. So here you can also use the zoom function if you want to check more closely about the shapes. So you see here you have mostly like 3 or 4 are nicely shaped. This one is more intense. You can also go to this 3D view, and there you also see information how intense are your signals. So here you see 3 normal signals and 1 which is cut off. So this is a very, very intense signal and will most likely lead to the information that this is topped. And I will get back to this anyway with the when I am defining or telling you more about the fast scans. So overall, I would say this is a pretty good crystal. So what we now do is we go to the determine unit cell. You see the solution from the last time we did this. So I delete everything. So we go step by step. So it automatically loads in the frames or images it finds. So we have this name. This defines the run you're currently using. So it's the first run and it starts with the first frame. It shall use for the unit cell determination the first run, and out of this the following 20 images starting from 1. It will take all the reflexes into account which have this, which fitting this criteria. So it has to be at least a minimum I over sigma of 10. If you have icing or you want to exclude some shells, you can also add them here. And all the reflexes it will harvest, it will store them into this gray group. So we leave it as default, and you see here now that it has harvested 442 reflections. So to get a good first estimate, I would always try to get at least more than 100 reflections. So you would now go to index. We want to take the same criteria as for harvesting into account and go to all the resolution range it will suggest here. We have different methods for searching the unit cell. We take the default values. Most of the time, in over 90%, they are totally fine. And you see here that you have a nice fitting unit cell found. So what does it tell you? This is the real space. This is the reciprocal space. And with a deviation of 0.1, it could already assign 95% of all reflections. So it's 422 or 442 reflections it could successfully assign to this unit cell it found. So this is very reasonable. So we accept this solution. We now click on refine, and what it does, it will take the reflections into account, and you see here now the deviation of the unit cell parameters. So you see here we are in a very, very good range. So only 0.002 plus minus in addition to this unit cell parameter. So this is very good. If you are more into graphics, you can also check this histogram window, because what you see here is, again, this is the real space, this is the reciprocal space, and what you want to have is that they both are, the maximum is as close as possible to 0. Because this means the reflex that you observe is where it should be. So where the estimated position should be. So this is at 0. And you have little to nearly not existing signals shortly or close to 0. So this is very, very good. The same is in the reciprocal space. So here you see, because the HKLs are always integers, and they should always be at the intersections of the grid. So here you always want, as well want to have them as close to 0 as possible. So overall, with this information and this information, you get the very good feedback that the crystal we are currently using has very good quality. So what we do now, we accept, and we go to the Bravais lattice selection, and always ensure that the criteria it lists here, that it is reasonable. So From your initial unit cell, you see we are very close to 90 degrees in all angles. So orthorhombic is definitely a reasonable solution. If you would have, for example, 5, 9, 30 or 40, this is a unit cell where you should be aware that most of the time there might be some twinning, what's or not. So, so always check that this is reasonable, the values, and also the solution here. So overall, the angles are close to 90. That makes sense, and also the length are in a region and comparable to each other. So you are not 5, 9, 40, but 18, which is absolutely fine. So with that, we accept. We can refine if we want to once again. So it will now take also the Bravais into account. You can refine, and you will get now with the orthorhombic P, the deviations, and you see they are even better than before. Before you would start a measurement, I would always recommend to make a cell check and check if the substrate you are about to measure has not been published so far. So we have different databases here. The CSD is not installed because we have a test PC currently attached to the instrument. But if you download CellCheck CSD from the CCDC homepage, you just install it and it will automatically be implemented in Apex4. So you will have access to the CSD database. The CSD database, COD database, the first time you will open this plugin, it will ask you if you want to install it. Click yes. It will take 10 minutes. Then it will install the database. And you see here now that you have some entries. If you double click it, it will redirect you to the homepage and will show you the entries. And you can cross check if it might be the complex that you or a person you are measuring for have submitted to omit that you will remeasure something which is already published and you will just lose precious measuring time. The other two databases, this is the database. Everything that has been processed on this PC locally will be stored in this database. You can also define an own database, either also locally on this PC. For example, you have one folder where only publishable structures are. So you can, if you find it here and not here, you know, okay, I have to remeasure a good quality crystal for publication. Or you can also use a directory on a server, for example. So you can cross-check if anybody in your whole institute has already measured it. Okay, with that, we are basically done with the determination of the unit cell and checking if it's already published. So we can close it. And the next step is, okay, we are happy with what we saw. So now we would go to calculate strategy. So if you open it, the instance of Apex will communicate with the instrument to get hardware feedback. What we now do is we click restart. And you see here, it already suggests you a resolution it could collect. For that, we would go to a reasonable one. I have to. Basically, for molybdenum, I always suggest 0.75. With the fast scan, you most of the time have the ability to already make a pre-structure solution. So you will also get a hint about the space group most of the time. So if you know that your structure is then chiral, you can select it here. Of course, you can also say centrosymmetric. You will also get the information, how much of the Ewald's field it will collect. In that case, of course, for centrosymmetric, it only needs half of the information. So it will here now collect an octant. If you go for chiral, it needs a quadrant, so double the amount. So here is the unit cell you determined earlier. If you click apply, you can now go to the determine strategy. As said, 40 millimeters is totally fine with the detector distance because the spot separation was well enough. And you know that your unit cell is reasonable. I would say it's medium or even a little bit smaller. So if you have a huge unit cell, you will also, of course, will get the spots will closer or will close up to themselves. So you might consider also collect data at longer detector distances. Here, if you have a cryo attached to your system, it will automatically recognize it and by default will be activated. This function will prevent that it will calculate a strategy where chi is either perpendicular to the cryo stream or directly in line of it. And this is only to not provoke icing on your sample. You can fiddle around with the overall completeness you want to have. You can also adjust the minimum multiplicity you want to have for 90% of your overall data. So you can say here, okay, please collect at least so much that I have a multiplicity of 3 for the 90%. If you have one large unit cell length, you can also check this one. It will then take into account that it will not rotate or will not do the rotation direction with the longest axis, so that you will force or that you will provoke overlaps. So you can also check it here if you have super long unit cell length present. So you click on OK. It will calculate. What it will do now, it is back and forth asking the hardware and the instrument, okay, I would do this run. Would it drive into collision? No. Okay, I check it. I will do the next run. What's or not? So with that, orthorhombic is has quite a higher symmetry. It doesn't need so many scans, so it was pretty fast. You have two ways. So you have, again, a graphical output. You have also a text output. It will do 2 fast scans in advance. They are here. Then it will do 1 phi scan. And in this phi scan, it will collect 5,124 reflections, of which 2,440 are unique. You already, only with this scan, you will get a P90 multiplicity of 1.3 and an average multiplicity of all data of 2. The overall completeness in that case would be 97.64. Therefore, it will add an additional phi scan. In that, it will collect 6,274, of which of the missing ones it will collect 58 unique reflections. It therefore will raise up the P90 multiplicity to 3.1, so above our criteria, an average multiplicity of 4.6. And you see the same here. So the P90 multiplicity will be roughly above 3, and the completeness is close to 100. So we are happy with that. Very important is, okay, why don't we have 100%? And you see here, there is one missing reflection, and always check, okay, this reflection is in the beam stop region. So you will not get it, independent on how much you try and to recalculate the strategy. Again, we also have a nice graphical tool which will help you to identify how the strategy will be collected. So you can see here the unique reflections. You have here some drawbars and the legend of multiplicity. So you can define also a region which tells you, okay, from 3 to 5, please show me all unique reflections that are going to be collected. More important, as said, might be the missing reflections. And you see here, there's this inner 3D sphere. This is the beam stop region, and this reflex is exactly located here. So you will not be able to get it. Another interesting feature in this is you will see the phi axis. This is the black one. You can activate, deactivate it. And especially for needles, that can happen with the mitogen loops, that you will that they will slip through the force and will perfectly align themselves to this mitogen loops. And then most of the time you have aligned one of the axes to the phi axis. And if you will then try to measure P1, there will always be a cone of reflections that you can't reach. So always be aware if you have low completeness calculated and you don't know why, then it is always worthwhile to check this reciprocal lattice view and check if this phi axis is aligned with one of the axes you find here. Okay, I think we are pretty happy with what we see. So what we can do now, we will go to the select scan parameters. So for molybdenum, I would always suggest to collect 0.5. This is the slicing, how many, in which step size you will collect. So it will do all the scans in 0.5 degree scans. So it will 0, 0.5, 1, 1.5, and so forth. And overall, we want to collect all the frames with the same global exposure time of 1 second. More important for copper measurements, because there you see here, it will do 2 scans with the same theta position. Because it's a molybdenum source, we have a contracted or compressed diffraction pattern, so you can collect all the resolution you want with 1 2 theta setting. With copper, you most of the time have a expanded diffraction pattern. Therefore, you will most of the time need to collect at different 2 theta positions. And what happens is that your inner reflections at lower resolution are always, or most of the time, more intense than the high-res resolution reflections. And to get reasonable data in all shells, there is this 2 theta dependent scan time function. Because if you would have different theta positions, it would extrapolate for the lowest 2 theta times. Of course, you need less exposure time because the reflections are more intense. And for the higher 2 theta positions, you could then, for example, go to 10 seconds, and it will extrapolate if you have different theta positions from the lowest to the highest exposure time. Since we only have 1 2 theta position present, this function, and you see here it's grayed out, so it would not make any difference to the parameter settings we have here. You see here it will already be done in 16 minutes. Of course, you can also define, okay, please calculate a strategy which would be done in 2 hours. Then it will do 12 seconds. And you see it roughly done in 2 hours. You can also set a time when it should finish. So for example, okay, tomorrow, until tomorrow in the morning at 7, I have a time slot. So please use the time to collect this data. So I guess 1 second was already okay. We accept, and you see now also this plot has been updated. And you will see all the details again in this table here. So this is the determine strategy plugin. So what we will do now is we go back to the run experiment. And I will append. And finally, I will now come to the points of fast scans. So fast scan is basically a substitute for the matrix runs. So and with previous detectors and generations of diffractometers, most of the time you would use matrix scans because you would save time, and you will do, for example, 20 or 10 degree scans in 3 different positions of the goniometer. So you will get 3 different positions of the Ewald sphere, and out of that information, you most of the time get or can determine at least the unit cell. And then you could cross-check with the databases if this was known. Since we can now do shutterless collections, we now do most of the time fast scans. So this is a 100-degree scan. So you will start at 0. I guess this is a phi scan. So we will do start with at phi 0, and you will do 100 degrees with 1 degree steps, and you will there get half of the sphere. And with that, you can not only determine the unit cell, but as said, you can most of the time also do a previous structure solution. And Pratap will later on show it graphically also on a slide. Not only with the additional information you get, you can also use fast scans to re-import reflections which have been topped in the in your experiment. So if you look closely at the BIS, you will see here it collected 180 frames out of 177 feature at least one reflection which was exceeding the dynamic range. So this can't be or will not be accounted in your data processing later on. So to get complete data, you will do the fast scan, and in the scaling later on, you can re-import those reflections which have been topped from the fast scans you collect here. And to ensure that you really get all reflections, you have different setups here. So you have this with the detector modes. So the sensitive is our photo counting mode. This is very, very excellent to be used for weak data. Or I always try to collect your data if possible in this mode, because it is more accurate. So the data you will collect is more accurate as the dynamic mode, which is the charge integrating mode. The charge integrating mode has the advantage that it has a wider dynamic range. So if reflections will be topped in your sensitive mode, you would be very good to recollect the data in the dynamic mode. If you will still get some top reflections in the dynamic mode, you will have the additional option to attenuate your primary beam. So with that option, the software will trigger an attenuator to be rotated into the primary beam, and will then lower the primary beam intensity a little bit to further allow the recollection of topped reflections. So most of the time, I would emphasize so check closely after your fast scan if any frames have been topped. If not, you don't have to bother to recollect them with dynamic or what's or not. If most of them are topped, you can either decrease the exposure time or ensure that you will also add a fast scan in a different detector setup. What else can we do here? You can basically control everything necessary for you. So for example, you can collect a crystal video afterwards. I would always suggest to do so, especially if you have a cryo attached, because for the crystal video, it will drive into perpendicular to the cryo and will do a 360-degree scan. And sometimes it happens that it will have icing afterwards. So please always do the crystal video afterwards. You can control the thermostat. You can say, okay, please, I want to go to 150K in a rate of 240K per hour. Then I want to equilibrate for at least 2 minutes. And then, for example, we will switch to copper and then do a fast scan again. After that, please drive my crystal to a certain position and turn off the thermostat. It will ramp it to room temperature and then shut it down. If you're happy with what you have programmed so far, you can validate. It tells you, okay, everything is valid, so you will not drive into any collision whatsoever. Don't worry if you haven't validated yet. If you click execute, it will do it anyway. So this is internally implemented in the execute as well. And it will give you direct feedback if there is a problem. For example, what you have programmed in line 4 is not valid. With that, you would click now execute. It will now tell you, there's you already collected frames, and I found frames in your folder with run 1. So with your current setup, you would override what you already did. If you want to, just click yes. In that case, we don't want. So we increase the number of the first run. And since we already collected it, we just deactivate it. So now we would execute. There's no error or no message popping up. So it now will start your measurement. And with that, I guess I'm done so far with my part, and will give back to Pratap.
Yeah, thanks, Karsten. Thanks for the excellent description. So let me share my screen. I hope you can see my screen back again and hear me. Right, Karsten? Can you please confirm?
Yes, I see it.
Okay, thank you. Okay, so Karsten has put us for the data collection. So just one slide I just wanted to explain for the beginners is if you're screening the crystal at the beginning, so if you see the ideal single crystal, you should have a spots well separated and discrete spherical spots you should see. That's an indication of a very good crystal. If you see something like this, kind of a diffuse and weak kind of spot, so then you can consider this as an average or a moderate quality crystal or a weak crystal. So if you can't grow a better crystal, so then try to collect the data on this so you can deal with our software to get improved and try to get something out of it. But if you get something like this as kind of a deparing, so then this is not the right machine. So you need to measure that in the powder XRD. So that's kind of amorphous or polycrystalline material. Carsten already explained you in very well that what's the difference between fast scan and the matrix scan. So just in the graphics, I just wanted to show you. By now, if you are using Apex 4 in your diffractometer or the latest version of Apex 3, so then the determine unit cell plugin automatically takes you to the fast scan. So what basically it does is it collects the almost the rotating 5 to 180 degree and collect 1 degree images for each almost full sphere of data. Whereas the same amount of time you were investing before as a default 3 different orientation of crystal, approximately around 30 frames. So you were able to get quality and unit cell, but now with the automatic determine unit cell, which includes the fast scan, will help you to get more number of reflection, especially useful for a chemist. So if they want to know within few minutes, like whether their structure is the expected compound, whether it's a right structure, so they can get the preliminary structure in few minutes using structure now, or just a determine unit cell plugin, or you can, the other advantage clearly explained by Carsten about overflow protection. Along with that, you also know the symmetry, so you can exactly define or tell for the strategy optimizer that whether it is a centrosymmetric or not, whether it's a monoclinic or not. So we can be sure of determining the strategy as well now. So these are the many advantages you get from the fast scan. Okay, so however, let's move to the processing of the data, because already we have put it for data collection and we know the crystal is good. We have collected the data, so we need to process. So the data processing is like 3 or 4 steps. One is the integration, second is the scaling, and third is the determining space group, fourth is structure solution and refinement. So in the integration in Apex 4, the software, the behind which works is Saint Plus. Okay, so for scaling, we use either SADAPS or the numerical phase absorption correction. And then determine space group, we use XPrep or determine use space group plugin itself. So all are included in Apex 4. So basically in integration, what it is doing is it actually estimating the raw intensities of your Bragg reflection measured during your experiment. For that, what you need to estimate this Bragg reflection to create a model, so what you need is you need to know the information about unit cell. So that is the orientation matrix you are determining. So unit cell is nothing but an orientation matrix. Along with this unit cell information, if you know the detector to crystal distance, along with you can predict the Bragg reflection position whenever you rotate your crystal. So using these information, crystal to detector distance and the orientation matrix, you are predicting the Bragg reflection and trying to model, trying to estimate the raw intensities of the Bragg reflection which you have obtained. What's going on in behind when you start an integration is it actually first goes for each frames and makes an initial background. So because you need to subtract this background, and then it creates an active pixel mask. which will mask your, the unwanted areas. Like if you have a beam stopper, you definitely have a beam stopper, it masks the beam stopper. And then if it is any, if the reflections are outside the active area, so it masks those things. And then if there is any shadow coming from your cryostream, it also masks up. So it does these things, and then it reads in your unit cell, and then it looks for a spot shape profile. How does your reflection looks like? And then it integrates in a particular box, and then it corrects for your Lorentz and polarization correction and any experimental errors which might have occurred during this process, and then make the raw intensities at the end of your integration. I have few slides to show, because when I tell you need to change some parameter, you need to change some tweak in some parameters. So then you need to know about those, what exactly you are doing it. So to explain that, I have got some few slides here. So this slides explains you about the integration box, which you can find under the refinement option. Actually, what it does in integration is, the reflection goes into several images. So the one reflection may not be finishing in one single image. So it might go into several images. And it's, this is a Gaussian shape reflection. So it occurs in one particular position, that's the position of Z, and then it integrates that particular reflection in X and Y box. Okay, so this is the integration box which you define, and you integrate the reflection within this box size. So if your model profile, if the box size is good, then you see the green circle while you're integrating. That's the output you will see. If the box size is too small, so then the green reflection should be inside this box, tries to come out, and it will become white. So you need to change. Where to change these values is, it's the initial XYZ box size. Actually, software for each data, it estimates or gives you the box size automatically. So you can start with your integration by using default values. So then if you know that the box size is too small or too big, so then try to come and go under refinement option and try to change these parameters under refinement option. I have told you that one particular reflection goes into several images. The sign looks up to 15 images. So it looks from the center of the reflection, 7 frames on the left-hand side, 7 frames on the right-hand side. So totally 7, n is equal to 7 here in the image queue. The default value is 7. So that means 2 times 7, 14 plus 1, 15 images. It will be looking for each reflection up to 15 images. If reflection is too strong, or you might have made fine slicing of data, then one particular reflection goes beyond 15 images. If it is the case, if you are using default values, so then it kicks out that reflection. It does not count in the integration. So that is frame queue size exceeded. So then at that time, you need to modify those numbers. So for example, in this case, I have modified up to 20. So if I use 20 means it will almost look for one particular reflection almost up to 41 images. Then you might ask me where I will need this. So you will get this output, after the integration, the LS file where it will show, and also there is a graphical feedback you get. I will show you while doing it, that if there is a frame queue exceed, you can see it and you need to modify those things, especially when you're doing the fine slicing data and when you're dealing with a strong reflection. So it might go up to several images. The third point is you need to adjust the model profile. So how does the integration happens? Overall procedure is, actually, if the reflection is strong enough, so then it just do the simple summation across. But if it is weak, so then it is like, as you can see, if it is strong, it just adds up. So if it is weak like this, so then it has to, it is trying to model profile fit those particular reflection. So to make this profile fitting, so you need a reference. So this reference is also defined by your own data. So that is based on your strong reflection. So there is a criteria also within your data to look at those model profile. That is under here, model profile, intensity sigma lower limit and intensity sigma upper limit. So based on these stronger reflection, it gets a model and tries to fit those models into your weak reflection. These are the two ways of integrating your data. So if your data is pretty weak always, so then try considering changing this upper limit and lower limit as well. Because if you use this, if your data is already having a I by sigma lower than 6 or 7, if you use this 10 and 8, so then it won't find any good model profile. So you need to reduce these values as well. I will show you where to modify that as well. And then another thing is, so if you virtually in the same program, the detector is divided or considered to be divided into 9 different regions. That is basically at the center one region and 8 separate regions across it. So if the reflection is strong in all the regions, so then it doesn't make any sense to blend the profile from all regions. But if your reflections are weaker at different regions at higher angles of the in the detector, so then what you have to do is it's better to blend the profile from all detector regions. So that means the whatever the best reflection which you have used from the lower resolution or strong reflection, based on that it tries to fit the model profile for all regions. Otherwise it will try to look for better reflection here to find out the model. So then it may not be so good sometime if you are dealing with the weak data as well. So and then you have also this background correction. So that is, use best background and use best plane background or use recurrence background. Recurrence background is mostly used and it is actually an average background created over several frames, whereas best plane background is in this case what it will do is the program goes up to each image and near each reflection and tries to picks up the pixels around it and tries to remove the background from each profile. So that defines the best plane for each background. That's the best plane background. Where it is used in best plane background, when you have a too contrast background. So when you have too much 2 theta offsets, you can have a different background. So then you could consider using best plane background. Or when you have a ice ring problem or some run affected by some mounting material of some part of the crystal, so then try using best plane background. Otherwise recurrence background most of the time works better. Okay, so that's an idea or a hint, but it's always the integration is 2 or 3 times. You always have to do that, because if you know how to, if the data is weak, so you need to improve those parameters and to get the best out of it. Okay, so and this is the feedback you get from the integration as soon as you start. So there are several graphs to look at. You can available, but the most 4 important graph which we want to see is the average correlation coefficient. That actually tells you about the agreement between your model profile and the reflection. And typically, if it is greater than 0.7 or 0.8, then consider it as a good data and you have a better integration. If it is between 0.7 and 0.4 or 0.35, so then you know it's a moderate data or a weak data. If it is lower than 0.3, so then I think it's you are integrating in a wrong space group or data can be really poor. Okay. The second graph, which explains you about average intensity versus the I sigma versus the images. So that means on each frame, what is your reflection quality and the sigma of it. So if it is constantly you are getting the right values, 20,000, 30,000 counts, then you know you are getting a good reflection in each image, nothing has affected. If there is a sudden drop, then you know either crystal is moved out of this beam or maybe something has happened during the measurement. So make look at this profile always. And then the third graph is the average difference between observed and predicted spot. Actually, it represents the positional errors between your observed and predicted spot from your integration. So if our orientation matrix, if it is, it should be falling under 0. So that is a good data. If it is crossing plus 0.3 to minus 0.3, it's still okay. But if it is crossing plus 0.3 to minus 0.3, so then you know that you are integrating in a wrong unit cell or the data is not good. And third and fourth or final graph, which we are looking is a 3-dimensional this model profile. So if the box size is good, means you should see this box filled up with green spot. And then if it is trying to, box size is too small, means it will tries to come out and it will become white. Or if it is too small green at the center, you know the box size is too big, and then you might consider changing the box size as well. And then you always have, after the integration, you get the merge dot underscore ls file. That's the output file of your integration. So you can look at those files carefully, and then on the top itself it is written. I have highlighted in this red box. You can see the spots outside active detector area. So this can be due to the areas or the spots missed due to beam stop or your cryo seam or something else. There are some spots which might be outside your frame limits, or spots incomplete due to beginning or end of the run. And then there are some spots exceeding dynamic range. So this is the precise reason why we use fast scan if it is exceeding the dynamic range. So you can get back those using the fast scan, kind of a overflow protection. And then if there is a spot exceeding frame queue size, you need to change that frame queue from 7 to 10 or 15 or 20 to get back those reflection into play in, and then reintegrate the saint as well. Okay, that's all I wanted to show on the slide. So let's quickly work on a couple of data sets. So I have already got this, and we have also given you this data. This is a citric acid data. I have already, to save the time, I have already indexed the unit cell. Well, let's start with the integration. And before that, if you want to see the resolution, Carsten has showed you where to see the resolution. You can just see with this circle and then put it on your screen, and you can find out what is the resolution of your data, because I want to integrate the data up to what resolution I have the data. So I do not want to integrate the empty regions, okay, which just lead to poor completeness, which I don't want to do. So I want to integrate only up to what resolution I have got. Okay, so then I just quickly move to reduce data, integrate images. So generally you don't see the frames when you click on integrate images. So you just open integrate images like this, and you need to set up the resolution up to what resolution you want to integrate. I know this data has up to 0.75. I kept it 0.75. This is your unit cell which you have indexed, and then you just call in the runs, and then select all runs, including the fast scan I'm integrating, because I need to replace whatever the overflowed reflection. So that's why I'm including the fast scan as well. And then I can start the integration. And as you know, if there are certain frames are affected by ice, or certain frames are affected by crystal slippage or something, so then what you can do is you can tell the software that I want to integrate in the second run from first to 50, and then 50 to 60 I don't have any signal, so after 60 I want to integrate. So you can do that here, the controlling the images, and then you can also control the resolution limit for each run. Okay, so let's start integrating without changing anything. So whenever I want to reintegrate, so it will always ask me to overwrite. So I overwrite. If you do not want to overwrite, you just say it as in a different name. So you can see here, these are the 4 graphs which I was talking: average correlation coefficient, and then the average intensity versus the image, and then 3D profile box, and then also observed and predicted spot. If you want to see that, if your frame queue, I was telling you that you don't need to look at LS file, you can also have a graphs here. That is here percentage queue extent used. If I click on that, then I can see here the graph has come. That's a mean percentage of queue used. If it is around 20, 30 or 40%, it is okay. But if it is exceeding 60, 70, 80, try considering increasing the frame queue from 7 to 10 or 8 or 9. Okay, that's one of the feedback you can see from this graph. And then there is also one more graph which I like, is spot position overlay. So you can constantly see how the integration is going on each frame, whether it takes care of all the reflection which you could see here, or is it integrating in the wrong areas, not picking up the reflection. You can see that. Okay, this also gives you the live feedback of your integration processes. Okay, so all the time integration, you can see that there are some initial passes it is doing. That means optimizing the parameter, and then it starts the integration. Okay, let this run, and I just, let me share my screen. Okay, so I just want to, I hope I'm sharing back again, sorry. So I have another data here to show for the demonstration. But in this case, I we have not shared this data because it's a customer data, which is a bit confidential. If you look at this data, you see this is very weak data. So in the previous case, you are getting the data, always a little bit slow. Okay, in the previous case, you had lots of reflection, but in this case, you can see that reflections are pretty poor or pretty weak. If you look at the resolution is also around 0.95 maximum, you can see. Not within, below than that, you don't see anything. Up to 0.95, you can see resolution. So these kind of data, what will happen is if you encounter, so then if you use the default values, then you are in trouble. Like for example, now I have just got some unit cell just to save the time. I just want to go to integrate images here, and then I use just the default values. I don't change anything. Okay, so I'm not going to change any parameters or tweak in any parameters. I let it. I just want this to be run without any modification of the parameter, because I always do the initial integration without modifying any parameter. So I just want to start the integration. Hopefully it integrates, because yeah. So let's have a look. So you can see already the model profile, this one is showing white. That looks not great. And your correlation is 0. So that means you're completely doing something wrong. Okay. So you have either this is an indication that your unit cell can be completely wrong, or your data is already weak, but you need to see at least something, but you are seeing 0. So that means there is something wrong. So what I do is, now I know now I'm integrating up to different resolution. So I have to correct this thing. So I will put the correct resolution up to 0.95, because it also has a massive influence of your overall parameters on the later part. And then you can go under refinement option, because you have the box size is too small. You need to increase the box size. The first attempt I will make always is I want to double the box size. Then if I know that this is too big, so then I will make it half. So for example, now I want to double, so I will make 0.8. Sorry, 0.8. So just want to 0.8 and 0.8. So either you can enable box size while refinement, or you can fix this box size. So let us fix this box size and see what will happen. And then I keep it as the same box size throughout, with doubling the box size now, because it was showing white. And then next thing is I also change integration options, because I know my model profiles the data was very weak. I can't have the model profile which is 10 and 8. I can have lower values. How much lower I can go? I have tested already, so I will straight away go 5 and 4. But you can go step by step, like 8 and 6, 7 and 4, or 6 and 4, or 5 and 4. So something like this you can go. I straight away went to 5 and 4. Along with that, I also know that not all the detector regions have a strong reflection. So I want to blend those reflection from all detector regions. Okay, but reflections are not strong enough, so I don't need to modify the frame Q. So I keep it as it is. And this is a molybdenum data, and I do not see any too much background difference. So I keep it as a recurrence background. And then I say, okay. And then I just start integration. So let's see whether there is any improvement. I was showing 0. I was looking at the 0 values last time. Now I already can see it's coming slightly in the greener side, and I am looking at some values now. Instead of 0, you can see it's now doing the scan, and then you see almost like 60, 70. So you can see this up and down, because some of the frames do not have reflection. So obviously you see this up and down. So in some of the frames, you get the reflection where your correlation is around 60, 70%. So you are in the right path or in the right direction. This is how you tweak in the parameters of the integration to look at, to understand, or to enhance the quality of your integration to achieve a better data statistics, even for very weak data like this. So let this run. So we want to get back to this citric acid data, because the integration is finished. So now our aim is to go to the next step, that is scaling of your data. So that means you are doing absorption correction. So after the integration, you get the raw files. So I will take the merged raw file. Even the software default takes the merged raw file. Make sure you are having a proper Lave group and point group. 99% software picks up the right one. But if not, you can change the point group here. Make sure if it is a non-centrosymmetric, then use the point group 2 and corresponding to your crystal system. In this case, I will leave it just 2 by m because I don't know whether it is a centrosymmetric or not. The first step, I'll just keep it as it is. And then this is an additional spherical absorption correction you are doing with the SADAPs. So default value, by tried and tested with a lot of crystals, we have come up with value as 0.2. But if your crystal is too much absorbed and then you have mounted too much anisotropic crystal, consider changing this value. You will get this absorption coefficient value in your SIF file. And then you get the crystal radius, average crystal radius of your crystal, multiply this value, and whatever the value you get, you please put that value here and then redo the scaling. And then in the absorption correction, you have a couple of methods. The multi-scan is the SADAPs, and numerical mu from formula. It's not highlighted because only when if you do phase indexing, this you can do. Otherwise, you always can do multi-scan. And 90% of the crystallographer uses the 95% of the time they use multi-scan. Then under advanced setup, you can make an output file directly into unmerged HKL file, merged HKL file, or XD format, or modulated format for YANA. So you can make directly from here the HKL file. So now let it be by default. And then if you know here you are in integration, you included the fast scan, and then now the reflection you are taking back from the fast scan is during the scaling. So for that, the resolution cutoff you have put 1.5. You know, always the fast scan you have done with 1 second or even half a second. So the resolution will be generally poor. So that's why you want to use only the resolution up to 1.5. Sometimes you can use up to 1.2, no harm, but generally by default we kept it 1.5. So for a semi-automatic option, you have finish button, but we want to go through step by step. I will click on start. Here you get the diffractometer parameters. Here you get the data statistics. You get the reflection statistics here, and then the parameter you want to modify for the scaling, or how you do the scaling. Depending on your scattering factors, like what elements you have used and what's the size of your crystal, you can choose whether strong, medium, weak, or no absorption. Also, and again, you can adjust the restraint for ESD for scale factors as well. So let it run for the first time because you don't know how the data is. Data looks good because your R incidence and R difference is immediately R diffraction converts to one particular value within 4 or 5 cycles. So, and then converts to one value. So this one, the light blue color represents for only for the scaling, and the dark blue color represents for scaling along with the absorption. So if there is a too much absorption, then there is a difference you can see at the end, but if there is not much, so then it should converge to one particular value. And then along with that, if the scaling is going in a good direction, so you get this scale mean weight around 0.8, 0.9, and so on. If it is lower than 0.7, so consider that there is something wrong in your scaling, okay, or with the data. Click on next. So you get the graphical information here, R internal versus the runs, scale factors versus runs, number of reflections for each run, unique and observed, and then case factor for each run. That is represented in numbers here. And then you see, in this case, the fast scan has been included already. If not, you might see that this will not be ticked like this. So you need to tick and repeat the parameter refinement, okay, to consider the overflow reflection. And then here also you get the outlier rejection information. If you think the total number of reflections, there are too many reflections which has been rejected. So then you can try changing these values to get the better error model and then do it. So, and then finish your scaling. So basically it tells you what was your WR2 initially before scaling, after scaling. So it is in a good direction. And here it tells you how many reflection has been replaced for this data. 115 reflection has been replaced, which is a good sign. and then you get a lot of the diagnostic plot to look at. So for example, you have got this d-Dietrich's graph here, so which actually plotted versus I by sigma I versus the log 10 I. You should find a sinusoidal variation, and then it should go better than 30 for a very good data. So, but on a reasonably good data, you get around 20, 30 or so on, but you should see like that distribution. And spatial distribution, which is plotted against each run, you should see feature this maps without any features, not too many reflection. As you can see in each run, there are not too many reflections which are missing. So if it is, there is too much, so then either it is overestimated or underestimated, or something it is blocked by something. So make sure that you don't see too many reflections here. Then generally, if the scaling is good, means your chi-square statistics should be against the resolution should be 1. So it is in this case, it's 1, so it's correct. And then if you look at the intensity statistics, R int and R sigma versus the resolution at lower resolution, which is much better. As soon as you go for higher resolution, the reflection quality will become weaker, and then you expect slightly high R int and R sigma. And E square minus 1 statistics tells you about the symmetry of your crystal. So whether it is a centrosymmetric or non, if it is close to 1, it is centrosymmetric. If it is close to 0.75, it is non-centrosymmetric. If it is around 0.6 or 0.5 or 0.4, so then you know there is some internal twinning which you need to take care. And then to look at the scale variation, and ideally you should, the normalized scale factor should be falling on 1 for each run. So then the crystal is like a particular shape and it's isotropic. And then you have, if there is a anisotropic crystal like a plate or needle, one length is longer than one another one, so then you might see a sinusoidal variation. But if it is too much different in two directions, so then you see longer variation that will be reflected in your R internal as well. Okay, so just wanted to take you that, okay, this is good data, so you do not have any issues. So I want to take you through another data. So where is this? Probably this is the one. No, this one. Yeah, I think this is the another data. Again, this is a customer data which I cannot show you, so I have integrated and ready for the scaling. So I just start the scaling. I can see now everything looks fine. I just refine. Once I refine, I can see that the scaling is not at all smooth. It's converge, diverge, converge, diverge. And then my mean weight is also very poor. So in this case, I need to tweak in certain parameters. Like for example, I know this is a metal complex, so I use it strong absorber, and I can see there is a peak absorption effect. So I also try considering the recent ESD for scale factors. So I go slightly higher, like for example 0.01, and repeat the refinement. And let's see whether I can find any improvement in scaling, or it still goes diverging. Just a few seconds and you will get this update. Whenever you have too much absorption, you might see this kind of behavior. So you need to tweak in these parameters. Okay, now you can see after refinement, there was too much disturbance last time. Now you can see only one divergence, but still it is going in a good direction, but not great. So to improve, maybe I can go even further, restricting ESD for scale factor up to 0.02 and refine again and see whether really I can improve or not. I kept it as a strong absorber because this crystal looks like a very strong absorbing and then very anisotropic crystal. Okay, now it's looking better. It is much more smooth. After 4 cycles only it converged, and you can see this is also slightly improved, the mean weight. So go to next. Now look at this, your R internal is for all runs, it is good. For the seventh run, it is quite high, around 30%, rest are all around 10%. Why? Because this is a fast scan, so this is not considered. So to involve the fast scan in your scaling, so what I do, I just click on here, this is the seventh one, click, and then I do repeat parameter refinement, and then we'll see whether it has an effect on overall orient and whether it has an effect on mean weight as well. I was having 0.7 before, and then 0.72 it came up after my scaling, restraining my scaling. So I want to see whether there is still further improvement. Yes, I could go up to 0.8. So really, it helped me to get back those reflections, and then overall the model or the scaling looks much better now for a very turbulent data. And if I look at now the R internal, it's all along 10%, so which should be the case in all runs actually. If there is any too much variation between the runs, so then you know there is something happening with that particular run. So now it looks good. So finish. You can see you are started with 18%, it came to 8%, which is quite good, and replaced reflections are around 6, only few, but it is quite helpful. And d-matrix graph, if you look at, okay, it's weaker, but it is still in good direction. If you look at spatial distribution, of course, there are some reflections which are overestimated or underestimated, but that's reasonably okay, not too many reflection. If I look at chi-square, it's close to 1. Intensity statistics up to 0.9 or 0.8, it's quite good, and after that it is on the higher side. And then E square minus 1 statistics, it is telling it is centrosymmetric. If I look at scale variation, on the first run it is okay, but then on the third and fourth run you can see there is a huge diffraction volume change or scale, normalized scale factor is changing. That's because your crystal is too much anisotropic. Okay, so that is why you can see correspondingly your R internal also is getting fluctuating too much. So that should be avoided by, if you mount a proper size crystal, you can avoid these kind of fluctuation as well. And proper scaling and proper absorption will help you out. Okay, so now I just quickly go to back again for our citric acid data because we have finished our scaling. So the next step is I just want to take you through determine space group plugin. Yes, we have got the determine space group plugin. So now it is more informative. You get this quality of your intensity for or the reflection for overall data, and you get the information about total reflection. And then you can get this formula or the periodic table. You can add that into your formula directly. And now you know this is a monoclinic P, and it is represented here with a monoclinic unit cell with P centered, means all the atoms sitting at the corners. And based on that, if you want to reduce and see whether it is a triclinic is also possible, so you can reduce this threshold and do it as well. But to save the time, I just quickly move to the next. Now it is telling P21 by C is the space group. Yeah, and then you have an option to force any space group from the 230 space group possible. And then there are some informatory, planes, the reflection, how it is, represented or seen in your different planes. You can watch here. It's just for educative purposes. And then you can also reduce your threshold to find if there is any other space group possible or not. But based on this symmetry, that's it's only one space group it is suggesting, and with the combined figure of merit is also quite good. Click on next, you get the intensity statistics. If you are a number person, you can see in the numbers. If you are a graph person, you can see in the graphs here. And along with R int and R sigma, which was giving in Apex 3, now in Apex 4, you can also look at R rim, R pim, and CC half as well. Along with that, you get this main important factors of your crystallography or the quality of your data, completeness, redundancy, and it comes with a color coding as well. In the next option, you can find it better. You get this data statistics, and then if there is any warning, it will also gives you the warning here. And if it is green in color, so then you know everything is good. If it is yellow or orange, it's on OK or borderline data. If it is red, so then please look into that particular value. If completeness is less than 95 or 96, so then you get the red line and then you get the warning, completeness is poor. So it tells you about your quality of your data without looking at different files. And also you get if there is any transformation matrix applied, so you get the information about those things as well from here. And it also creates an ins file after you are determining space group. Now let's go quickly into the find structure, solve structure option. So where you want to solve your structure, so you just basically need the HKL file which you have created after scaling or after determining space group. So you get an HKL file, you use that, and then we have several methods to solve the structure. One is intrinsic phasing, direct method, dual space, and Patterson. So you can use either of those methods, but 95% of the time intrinsic phasing works out better. And then you gets the, even for the reasonable quality data also, you get the rightly assigned atoms as well. So which makes our life much easier. From here, we just can quickly go to the refine structure to further refinement and finalize your structure, because you already got your structure. So you can see it. Only thing is it randomly labels your atom, so with some different nomenclature. So you want to make it everything professionally and completely, like instead of O001, you want to call it as O1. So you can do if by hand with if it is only few atoms. If it gets more number of atoms, then you are in trouble. So that's why Apex 4 or ShellX they come up with the auto option, that is ShellX automatic labeling. You can label several atoms, hundreds of atoms together by just one click. You can do with residues or without residues. With residues will help you if there is 2 molecule or 3 molecule in the asymmetric unit and you want to have a constant labeling or particular labeling for each residue. So you can do that, or in this case without residues I will do. It loads, it labels within a fraction of a second or within a second. So it added the labels and it also put my INS file very organized and in very proper way. So now it looks better. So do the refinements. You go to isotropic refinement, starting with 14% with 1.54 as residual density. Load again, and then when you load the refinement cycle, you can see that you get another new balls, different colors coming up. These are representing the residual peaks or the Q peaks. You can control Q peaks with this bar on the right hand side if you want to see only few Q peaks, and then you can see what it is actually. So then you can do anisotropic refinement down to 7% with 0.78 is the highest residual density. That is because of your hydrogen, which still has to be added. Easier thing is ShellX automatic HFix you can do. You have fixed the hydrogen. You can do the refinement again. You are down to 4.4 with almost nothing left on the electron density. Okay, so this is how you refine your structure, and then you can also do further finalizing your structure, like try to refine until weight converges. If there is any hydrogen missing, please look at carefully and add those hydrogen. You can also have this kind of possibility that you can click on that particular atom and then add directly a hydroxyl hydrogen or whatever you want to add directly for that particular atom, or the methyl group or amine group. You can add whatever the hydrogen is missing. And then the important point is you also get this refinement history, so it will be always remaining with you. So you can have this for this what you call you can close your laptop and come back on the next day or few days, and then you might have done some 100 cycles, so you can start from any cycle. So if you have done mistake in 50th cycle, you can come back and start from 50th cycle, because it remembers everything and it stores everything. Okay. And then you can measure distance, measure angles, so create some contour plots, create some Voronoi plots. You can do fly checks if you can add some external program, which we have shown enough in our getting started workshop. And I think this will be recorded and you get this. I can see that I already ran 10 minutes over time, but I just want to create one report for you people, and then I stop it here. And if there is any questions, we can take for another 5 minutes before Carsten and me jump into the next workshop. Okay, so when you click on report, generally, if it is ActaSIF, it creates a SIF report. If you create apex3.zip or proteum3.zip, it creates a full informative, SIF, which gives you all the crystallographic information and how you collected the data, how you measured data, what's your crystal molecule you got, how is your packing diagram, how is your regular crystallographic table, detailed crystallographic table, coordinates, and all, and so on and so forth. So you get all these things, and it will be saved as an HTML format. You print that as a PDF and then take it for discussion or take it for thesis. So which was not there before. So now everything is on your fingertips. So of course, most of these parameters, especially this workshop we have conducted, because for an expert crystallographer, you need to know, because you deal with a lot of weak data and weak challenging data sets. So you need to know where you can tweak in the parameters to improve your data quality. It's not just like click, 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 and without knowing anything. You need to know everything as well. So that you can improve and enhance your quality of your data as well, or along with quality of processing of your data. So I hope we have given sufficient information in this workshop, and this will be recorded and which will be up in some website or on your desktop, who knows. So please wait for that, give us some time, we will get you this. So, and we always encourage you to work with the data which we have given. You can see under the website here, I have sent this link. You can get under Bruker user meeting, best practice protein, best practice in chemical crystallography. You have got these two data sets. I have worked with citric acid. You can work this paracetamol data and then try to process and tweak in some parameters and try to improve the data quality. So thank you. If there is any questions, I'm happy to answer.
Yes, okay. So there was one question. First of all, thank you, Pratap. Very informative. There was one question. If you could show once the phase indexing, and then that automatically there will be the option of numerical absorption available. I guess that's what by default they were asking.
I hope I have enough information on this data. So let's see. Reduce data, index crystal phases. Okay, so here I have got some, at least the advantage here I have shown, I think, in the best practice method, that you get this adjustment and zoom in and zoom out option as well. Now you can have a carefully look at your crystal for a better phase indexing, and you can also do this contrast brightness adjustment to have a better look at your crystal, and then you can just index your crystal phases however you wish. But of course, I just show it for practice. Okay, so this is not perfect one, but just if you have indexed wrong phases, you can, and then ideally you can click on the scale. Probably you need to reintegrate. I do not have information here, so this will be returned to your P4P file. Unfortunately, I do not have full data to show here. Carsten, do you have something readily available?
I guess I also included a video on the citric acid, so maybe you can
is it?
Just...
Okay.
I hope so.
Let's see. This is a citric acid. No. I think I changed that. Okay. Reduce data, index crystal phases. Yeah, here we have got some. So just for arbitrary, look at custom crystal. It's very small, so I just make it. Okay, let's quickly do it. I'm still not able to get out. Replace. Okay, I'm just getting one random size. Not so awkward. You can do it very patiently and very slowly and very closely looking at your crystal. Okay, so this is just an example. Removing faces, I have removed the whatever the wrongly assigned face, so you get the proper size of your crystal. Once you do this, I think you can just move on to your scaling here. Should be overwritten to your P4P file. Okay, then I go to scale. Not yet. I think you probably have to reintegrate. Huh? I'm in the wrong. What? Oh, sorry. I'm again in the wrong folder. You open. This is what happens. You open several Apex for. Okay, so reduce data, scale, index crystal faces. Wait a second, I will just do it for you. Remove faces. Okay, export P4P. So this index save. Then I go to scale. Yeah. When I click on scale, you can already get, if you have done the face indexing, either you can go to numerical mu calculated. So, and then you can start here. Same way how you have done it, or you can go to numerical mu from formula. So then you can start it here. And then you can give the exact formula of your compound, how many atoms exactly, so that will help you, and then update. Like for example, you have 4, you can update that, and then you see it exactly tells you how many elements you have. Then you click on finish or next, as you do it in exactly how you do it in the setups. Only thing is, now you considering the exact size of your crystal, exact shape of your crystal. That's what you are using for scaling. Whereas in case of SADAPs, you are just using the the approximate absorption coefficient from your learned thing, along with that some formula, the SADAPs formula. I hope Darshan, it is clear. If not, I can also show you once again at the later part. Okay. Anything else?
I guess so. For other questions, I already asked to send some data set so that we can have a closer look.
Okay.
Yeah.
Okay, thank you. So thank you, Darshan. So let me know if you finish, if you face still the problem, so I can hop on to your PC and see. Okay. Thank you. So thanks for joining in. I think we are already almost 20 minutes past. So Carsten and me has to quickly go to the next workshop. I think we will stop the recording here first. Stop recording. Thank you for